terminology that
All right, good morning, everyone. How did your homework go last night? If you had difficulties with any of the problems, please put your questions on the chat before we start. Anyone? Okay, so we keep going along the same line, of course, as will be the topic till the end of the semester almost. So yesterday we took one function and we find the slope of the tangent line. Okay, today we're gonna take another function and more. So I'm gonna try the following function: f of x equal, let us say, x to the power 3. And we are going to do what we did yesterday, basically, and find the slope of the tangent line. Okay, and then we find the formal definition. So my function of x equal x cubed, that's my function, looks like that. And the question is, we're gonna find slope of the tangent line at a specific point. Let us say one f of 1. So this is my point here, and this is my tangent line. And the question is, what is the slope? And as we said yesterday, for a slope, we need 2 points. We don't have 2 points on the tangent line, so we go back to the curve itself, and we start finding the slope of the secant line. And we try to get closer and closer to the point and find more secant line. And then we realize that all those become close, all those slopes become close to a number. This number is what we call the slope of the tangent line. So we will do this one problem numerically. So we make our table. So my function is x cubed. We make our table, and we make 2 because there is no reason we have to take slope from the right. We have to take slope from both sides, right and left. So this is my point Q, and this is the slope of PQ. So we start with some values. We compute them. So we can start 1.01, and we compute the slope. So the slope is the output at 1.01 minus the output at 1 over 0.01. We plug verbatim into the function 0.01. And then we pick up our calculator and we do the math. So we do the math on a calculator, and if we do it correctly, we get something like that. 3.01. It means if I take this slope here, let us say this point is 1.01. It means the slope of this point right here, that's the slope is 3.0301. That's really what we are trying to do. And then we move in closer. We move in closer to my base point 1, which is my base point. We move in closer and closer. So 1.001, we'll just do very quickly. And again, we compute that. And then we pick up the calculator exactly and we compute this. And if I did my math correctly, we got that much, 0.3. Okay. And we keep zooming in, and obviously as the x-coordinate become close to 1, those slopes become close to 3. And the idea, we have to do the same, but from the other side. So we approach it when x bigger, and we approach it when x is less. And we do verbatim. We take point Q, and we compute the slope, and we start taking point like 0.9, 0.99. So now I am computing the slopes from the left, here. And what we're going to realize is actually in this problem in particular, the slope will be a little bit like 2.71. So I use the formula verbatim, 2.9701. I compute verbatim. I get 2.997. So again, we get close to 3. So it's fair to say that the slope of the tangent line is actually equal to 3 in this particular problem. Okay. So intuitively, what are we actually, what we're really doing graphically? A little bit of intuition, we share it, and then we proceed. So I'm going to show you what we do graphically when we find the limit. Let me share the graph with you. Okay, so basically that's the function x to the power 3. So if we graph the function f to the power 3, and this is my point 1.1. Okay, so that's really the point. And that's the graph, that's the point. If I zoom in a little bit into the graph, intuitively, if I zoom in, so I'm going to zoom in tiny bit into the graph, a little bit. Means I'm seeing the graph under a magnifying glass. Okay. What do we realize the graph will happen to us? I'm not really changing the graph, I'm zooming in. As we zoom in into the graph, we realize that the function is actually becoming almost a line, closer and closer to a line. So if I want to find the slope of this line that the function is really becoming close to, watch, this is 1.1 because I'm zooming in. So if I want to find the slope of this line that the function is becoming very close to, not quite, it's curving, but very, very little, I take the 2 points on the line, like I take 1. And if this is 1.1, so this is really 1.025, and I find the slope of this line. That's the secant line I'm looking for. Now, if I zoom in a little bit more, the graph is actually even straightening more. So if I want to find the slope of the secant line, again, I will zoom in more, and I realize that the slope almost, if you watch very carefully, if you go by 1, the rise is almost by 3. So that's really intuitively what we are looking for. That's the slope of the tangent line. It's locally the function become more and more linear. And my question is, what's the slope of this line that the function become to? And to find it, this is the function. The more I zoom in near the point 1, the more linear the function becomes. So if I want to find the slope, I just have to take 2 points which are very close to the point 1 and find the slope of the line. That's intuitively what we're trying to do. We're really trying to find locally the function is almost like a line, and we are after the slope of this line. So to find it, I just have to take slope of secant line and zoom in more and more. So that's, I mean, actually on the graph, you guys can see it. We go 1 by 3. So that's really the slope of the tangent line we're looking for. Okay. So now we did a lot. I mean, we did enough of those. Now we're going to find the formal definition of the equation of the slope of the tangent line. So let's see now the formal definition, the definition that we're going to live by. So definition. Of the slope of the tangent line at the point. At a fixed point, at a point of a function f at a fixed point. So we have a base point and you're gonna find the definition. Very good. So the picture, and then the definition. So this is my function. Now the function is any function. This is my point, that's my fixed point A. And that's my base point. And this is my tangent line. Okay, so how are we going to define the slope of the tangent line? What did we do? We took a point Q, which is very, very close to P. That's intuitively what we did. So we take this point Q, and we took them from both sides. And we found the slope of the line PQ. We found the slope of this line. Now let us give this point Q a coordinate. It's very close to A. So we're gonna say it is A plus a little bit, A plus H. So A plus H, so it's A plus H. So H is actually from here to here. This little bit we attach to that. So basically, if I take Q to be 1.01 in the previous problem, where my P has coordinate 1, the H is the 0.01. This little bit we add to 1. In this case, the H is 1.001. Can you put up a paper a little bit up like this, Hazem?
Yeah, that's good.
Got it?
I just needed to read the definition of the...
Yeah. For the slope of the tangent line of a function f at a point. Is this better? Okay. So H, this is a little bit that I'm going to add to A. And I'm going to compute the slope of PQ. So what's the slope of PQ? Okay, this is the picture that we've seen. It's from here to here, it's H. That's really the rise if you want. And this is, so that's the run and that's the rise. It's the change in F. That's F of A plus H minus F of A. And this is the little h. So the slope of my line PQ is what? Now in general, because we have to build the definition, it's nothing more than F of A plus H minus F of A, which is really the rise if you want, or the change in output. So you can sometimes call it the change in output if you want, divided by the change in input, which is A plus H minus A. So which is A plus H minus A, which is nothing more than H. So the slope of the line PQ is nothing more than this ratio between the change of the output over the change in input. That's really what we're gonna call that, because delta X is how much the input change as we go from A to A plus H. Okay. Now, when the idea of the tangent line is basically we want the point Q to become close to P. So what we did, we took point Q like a little bit farther away from P, then we got it closer, then we got it closer, then we got closer. That's really the intuition. So when Q become close to P, this occurs when H is becoming close to 0. So Q become close to P when this difference right here is actually shrinking. The smaller H, the closer Q is to my point P. That's really the picture. So as Q become close to P, H become close to 0, and the slope of the PQ become close to basically the slope of the tangent line. Of the tangent. So here's the definition of the slope. So now formally we're going to define the slope in the following form. So the slope of the tangent line That's the formal definition. Slope of the tangent line of the function f at the point A, f of A is defined by the following. We compute the slope of the secant line. These are the line MPQ over H. But we want to see what happened to those slopes when H becomes smaller and smaller, because we want Q to go toward P. So we define to be, so in math, the idea of letting H is the notion of a limit. And we compute the limit as H goes to 0 of f of A plus H minus f of A divided by H. And that will be the general definition of the slope of the tangent line. So the slope is defined to be, these are the secant line. And this is what happened to them when Q is becoming closer and closer to P. So it's the limit of secant lines. Okay, before we start really, of course, doing problems, and I will go back to the picture a little bit. All right, are you guys fine? I'm gonna go back to the picture a tiny bit. If I take my point Q to the left here, because as we said before, we take them both to the left. And what happened to H in this scenario? What can we say about H? So I take you back to the previous problem. When my point P has coordinate 1, and I point to point Q to be to the left of 1, like point 9, what is the H in this particular problem? What's this idea of H, this little bit that I'm moving away from 1? Can anybody tell me? What do you think in this scenario is my H? The H is how far?
A 1?
What?
Is it a 1? Because it's getting closer to 1? Or...
Yeah, but what's the H? The H is how far we are from 1. That's the H. The H is how far we are from 1. Like in this case, that's the H, from here to here. So how far are we from 1 here? This is the difference. 1 is nothing more than 0.1, right? That's how far we are from 1. That's what the H is. And but it's actually not 0.1, is minus 0.1. So right here, my H is negative. So because when I'm taking my H here, this is my H is gonna be negative because I'm taking A, I'm taking away a little bit in this scenario. So if I take in this scenario, this is 0.9, it means it's 1 minus 0.1. I'm taking 0.1 away. So the H here is negative. If it's 0.99, this is 1 minus 0.01. So my H is minus 0.01. Right here, this is 1 minus 0.001. So my H here is minus 0.001. So when I go to the left, the H has to be negative because I'm taking a little bit away from A. And from here is H is positive. So H is how far away I am from my base point. That's really H, how far away I am from my base point. It's this a little bit. So I move a little bit away from P, a little bit. The horizontal distance is my H. Okay, so now we're going to do one more problem, and a simple one, but I want to do it numerically. We're going to do it algebraically in 2 different ways, and then we practice this idea. So I'm going to go back to a f of x equal x squared because I want a simple problem algebraically. And I'm going to use this formula verbatim. Okay. So example, we're going to take the function f of x equal x squared. And I'm going to find the slope numerically. And I'm going to find the slope algebraically. So f of x equal x squared. And the question is, find the slope of the tangent line of f of x equal x squared at the point 2 f of 2. So if I put 2 here, I have to put f of 2, which is 4. Okay, and we do it first numerically. And I try to do it fast numerically, and then we will definitely do it algebraically. So numerically, so that the picture in my mind, I like to draw the picture so to know what I am doing. So this is my function f of x equal x squared. That's my base point. So my base point here is 2. This point is on the curve. And I need to find this line, which is look very much like the curve itself. So we're going to take point close to it right here, find those slopes, and see where they get close to. Okay. So as usual, we take our table, and I will not do it in a tedious way, so we're going to make it as fast as possible. So this is coordinate of x, of q, but I'm going to add a little line here. This is the h, which tells me how far away we are, and this is the slope of pq. Okay, so we're going to introduce h just to know exactly what the h is. So let me start by taking, let us say I take 2.01. So my base point is 2.01. So this is here, 2.01 right there. So my h is how much I have from here to here. That's really the h, how far away we are. So the h in this scenario is 0.01. That's the h. That's the little bit I'm going to add to 2. Now the slope is easy because this is the value here, minus 4 divided by 0.01. And we can do the math. So we are going to do the math, and if we do it, you guys plug in the calculator, you get 4.01. Okay, we take 2 more values. I want to emphasize the h. I'm going to zoom in. So in my mind, I am zooming in into the function. And I'm zooming in. And the more we zoom in, the more the function is actually looking linear. So if I zoom in a little bit, I'm right here. My h now is the difference. My h is the difference, 0.001. And I compute my slope. And as you realize, every time we're doing the same thing over and over and over. So that's repeating ourselves. That's why we have to do it algebraically, because this is kind of, you know. So as this h getting close to 0, my slope here seems to be getting close to 4. Okay. Now we do it from the other side just to make sure, or to get into the habit. So now here, basically here I am taking h positive because I'm taking 2, add a little bit. Now I'm going to take 2, take away a little bit. I'm going to take away a little bit. So now h negative. So this is x coordinate of q. This is my h, and this is my slope. And let us do that. So if I take h to be x coordinate, so let me take it to be 1.9. So what is my h in this scenario? What is my h in this scenario? So 1.9, it means I am right here. So that's the point 1.9. So the h is how much away I am moving away from 2. So the h now is the minus 0.1. So because this h, this point here is 2, so 1.9 is nothing more than 2, but you take away a little bit. You take away a little bit. Okay, so now the slope is nothing more than what the slope is, divided by minus 0.1, and this is 1.9 squared. And at this stage, I do the math, and if I do my math correctly, I should get the 4 minus 0.1. I think I will get 3.9. And in a minute, you will see where those numbers really are coming from. Very good. I will take one more, 1.99. So now I am zooming in right here. The h is how much is from here to here, how much we're moving away from h. So in this case, so 1.99 is basically 2 plus what? So that's really the h here. And if you do the math, is 1.99, you're taking away 2 from it. So it's minus point, in this case, 0.001. And now let us compute the slope. Sorry, 1.0. So let's compute the slope here. So we will have 1.99 squared minus 4 over minus 0.01. And I will do the math here and I will get 3.99. Okay, so that's the numerically. So as h basically again is getting closer to 0, my slope is becoming close to 4. So it's fair to say numerically as I say, numerically that the slope is equal to 4. So the slope of the tangent line numerically is 4. It's 4. Now we have to do, as you realize, I'm doing the same thing over and over, which is really, really kind of boring and it's tedious. So the question is, why don't we do it algebraically? And that's really what we will be doing now. So algebraically, and what do I mean by algebraic? Okay, let me go to the definition of it. And that's what we are doing every time. I mean, I'm computing slopes by assigning to h specific value. Now, algebraically, it means I'm going to use the formula verbatim and try to do the same problem by using this particular formula. So let us see how to use, which is a formula that is so important. Okay, so we're going to do the same problem now algebraically. So this is my picture. I will draw the picture again and what we do. So it's the same problem. I'm not changing, and I will take you back to what we did to compare what's happening. So again, we're going to do the same problem algebraically. So my function, I'll keep it here in front of us. X squared, the point I'm interested in is 2f of 2. That's my point. And so this is my function here. This is my base point. This is my slope. And this time, instead of doing it several times, we can do it at once. So what is the logic? I'm going to pick a point here. And this is my base point 2. This point here is 2 plus h. And I'm going to compute the slope of this line. And then I'm going to ask myself, when this little h becomes close to 0, what will happen to those slopes? So let us compute the slope. So the slope of the tangent line is at the point 2f of 2 equal the slope of the secant line. So the slope of the secant line. So now instead, as I said, doing it a million times, you do it at once. And then after we compute the slope, we say, okay, let h become close to 0. Very good. So now we're going to compute that. So this is equal. Now a little bit, don't worry about the limit for now. We'll take care of that later. What is f of 2 plus h minus f of 2? All right, I put in the function f of 2 plus h is 2 plus h squared minus f of 2. If I plug in 2 here, I will get a 4 divided by h. Okay, and we have to see what happened to that. So let's see this is equal to. Now we know from limit, that's where the limit is going to come back. When h becomes close to 0, the denominator is 0. The numerator, that's going to give me 4. The numerator goes to 0. So it's really a 0 over 0, basically. So we have to manipulate algebraically. So in this problem, the manipulation is not hard. So we're going to take the limit. And we're going to expand this term and see what happens. So this is going to give me a 4 plus 2 times 2, 4h, plus h squared. So I'm basically distributing this term, minus 4 divided by h. We keep going. So it's the limit as h goes to 0. So I try to remind you that this is always, those are the slope of the secant line. Those are the slope of secant line, PQ. So that's what we are computing so far. Now we simplify the 4 and the 4. We get 4ho plus h squared over h, those quantity that we try to practice with. Remember, those are still the slope of the secant line. So this will give me the limit as h goes to 0 off. Now, usually when you do the math correctly, you should be able to factor out the h. If you can't, it means somehow your math was not correct. So finally, this is equal to the limit as h goes to 0 of 4 plus h. Okay? So before we find the limit and we find the number 4, let's see what does the 4 plus h represent. This 4 plus h is actually the slope of the secant lines for different value of h. So let me go back a tiny bit to here, to the previous part. And you can see what's really happening. So watch carefully here. Actually, that's the piece I want. I'm gonna totally, this is the piece I want, right there. In this case, that's the previous one, when I did it numerically, my h was 0.01. What was the slope? 4.01, which is the 4 plus h we got from here. That's exactly what's really going on, but here we're doing it in a more abstract way. When I took h to be 0.001, the slope is 4.001, which is the 4 plus h. So the 4 plus h is actually those numbers, but instead of taking specific value of h, we did in a more general context. So that's really those numbers right here. Again, I can go here. When I took 1.9, my slope to my h was minus 0.1. It means because I'm moving in the left direction from 1. The slope was 3.9, which is exactly, compared to that, it's the 4 minus 0.1, 3.9. So those numbers are exactly 4 plus h in a more abstract way. So that's why the idea is that instead of doing this over and over, we can just go back up here and do it in a more general context. And so finally, we compute this limit, which is going to be equal absolutely to 4. Okay, so that's how we're going to move toward algebraic way of doing those problems. Okay, any questions before we move on? Any questions? Okay, so now there is an equivalent definition of the slope, that it is equally important, and we're going to talk about it. So equivalent definition, it means it's the same definition, but I mean written in a different way. So our first definition was, that's the one we worked with, the limit as h goes to 0 of the secant line. That was really, so it's the change in f over the change in x. So that was our first definition. Now we're going to see an equivalent definition. So the slope of tangent. Okay. Now an equivalent definition. Of the slope of the tangent line. Okay, equivalent means it's the same definition, but it's written in a different way. All right, so here we are. Again, I'm gonna draw the graph. It doesn't have to be x squared, my apology, just any graph. And this is my base point. This is my point P. And this is my tangent line here. That's my tangent line. And the principle is the same. I mean, we're not changing, we're just gonna change names. We're gonna just say letters. So this is my point Q. And the idea is to compute the slope of PQ. And the way we did it in the previous one is that we took the point Q here, the point Q, and we called it A plus H. And the H is important. I mean, I like the H, even though we're going to do it 2 different ways, because the H tells me you're taking A, you're adding a little bit to it. So you're moving a little bit. So that's why this is a very good notation. Now, another way, instead of calling this A plus H, instead of calling it A plus H, suppose I just call it X. So I did not really emphasize the little bit. I call it X. Okay. So if I do that, what will become the slope of PQ? So the slope of PQ become the following. So this is, it's going to become the change here over the change here. It's the same definition. But now instead of calling this f of A plus H, it's going to become f of X minus f of A. That's what this will become. And from here to here, the change in X, it will be X minus A. So that will become X minus A. So the slope now will become f of X minus f of A over X minus A. That's the slope of the tangent line. Now, how do we get the slope of the, sorry, that's the slope of the secant line. How do we get the slope of the tangent line? What should we do? At this point, what do we need to do? Again, we take the slope of the secant. That's, but then what do we do in this situation? What do? We want Q to become close to P. We want Q to become close to P. How this happen in this new notation? Q become close to P when the x coordinate of Q, the x coordinate of Q become close to the x coordinate of P, which is equal to A. So in this case, the limit is actually not like the previous one. The limit when x, it means the x coordinate of Q become close to the x coordinate of A. And when this happens, of course, when x takes value close to A, of course, the H is going to become close to 0. H represents the difference between them. That's really what our previous H is. And that's our equivalent definition for the slope. So we can either use f of A plus H minus f of A, or we have to use this one. And I will write the other one and we compare them. We have to be very careful. So in the previous definition, so this is equal to the limit. So that's exactly the same thing as H goes to 0 of that. So let's not get the limits confused. In this case, the H represents the difference. So we want this to go to 0. So that's the H goes to 0. And here, there is no difference. Here, I'm taking the point X, and I want the X coordinate to become close to A. So that's the limit when X become close to A. And here, I want the difference to become close to 0. Right? Now we will take again the same problem that we've done before, f of x equal x squared, and we're going to find the slope again. So we did it numerically, we did it using this format. Now we're going to find it using this format as well. Okay, so we find it in all possible ways because both are crucial, absolutely crucial definitions. So I got back and I will take my function of x equal x squared. And I'm going to use this new definition to find it. So again, use the following definition. Of f of x minus f of 2 over x minus 2 to find the slope of the tangent to the function f of x equal x squared at the point 2 f of 2. Okay, so we're gonna do the same, but we're gonna use this different definition. Okay, so the slope equal f of x minus f of 2 over x minus 2. That's the secant type. But then it's the limit here. The limit of what? I want the x coordinate of q to become close to 2. Limit as x become close to 2. The rest is we've done before when we talked about limit, as you will see. So the rest actually is not going to become hard anymore. F of x is x squared. F of 2 is 4 over x minus 2. Does this one look familiar? It should look very much familiar. When x becomes close to 2, denominator gets close to 2. Numerator get close, denominator get close to 0. Numerator get close to 0. So to find this limit, we have to factor out. So we're going to factor out x squared minus 4 gives me x minus 2x plus 2 over x minus 2. Now the x minus 2 cancel. That's why we factor. We are left with the limit as x become close to 2 of x plus 2. And now this is equal absolutely to 4. Okay, so we can do the problems in actually 3 ways. Numerical is tedious, but we can do it in 2 different ways algebraically. Right? So now we're going to practice at least on 2 problems before the end of the hour. So first, I'll take a very simple problem just to say that the slope, when the problem is basic, it's not really a bizarre idea. So let me take a fairly simplistic problem, the following. Suppose now I'm going to take the function f of x to be, let us say I take it to be 5x plus 4. Okay. And the question is, find the slope of the tangent line at the point 2, no, I'm tired of 2. Let me take at the point 3, so fairly simple, and f of 3. Okay, so what do you think should be the answer? What do you think should be the answer? F of x is 5x plus 4. So if we graph this, that's a straight line. That's the intercept, and then that's my line. So if I'm going to find the slope, and that's a point, that's my base point. That's 3f of 3. And I want to find the slope. So what is going to be? And is it a surprise? As we said, we have to take another point and find the slope of that. That's really what it is. So we're going to find the rise over the run. So what should we expect? So let's do that. So the slope equal the tangent line. I'm going to use the plus h. Okay, equal to the limit. As h goes to 0 of f of x plus h, which is, f of 3 plus h, that's my base point, minus f of 3 divided by h. So this would be equal to the limit as h goes to 0 of 5 times 3 plus h plus 4 minus f of 3, 5 times 3, 15, 15 plus 4, 19, divided by h. Okay, so that's the limit. As h goes to 0, of 5 times 3, 15, plus 5h, plus the 4 over h. And that's the limit of 5h over h, which is actually 5. Okay. Is this a surprising answer? Is this a surprising answer? Yes or no? What do you think? Are we surprised to get a 4, a 5 at the end? No, absolutely not. Absolutely, that's what basically we should expect, because two reasons. First, when I pick the point here, I find the slope of the secant line. Of course, that's the line itself. So the slope of this line is going to be the slope of the function, which is 5. And then graphically, as I showed you at the beginning, what we are really trying to do is we zoom in into the function, and we're trying, when the function becomes more and more like a line, we're actually trying to find the slope of this line. But this is already a line, so we're done. The slope is the slope of the line itself, okay, which is the change of output over the change in input. Okay, so that's just to make sure that if the idea, follow our intuition. So if the function is a line, the slope of the tangent line is the slope of the line itself. Okay, now we're going to do another problem just to get the algebra going. I'm going to take a function, let's say, okay, let's say, I don't know, f of x equal 1 over x, for example. That's purely for algebraic reason. And my point of interest, let me take point of interest to f of 2. Okay, and my question is, we're going to find the slope of the tangent line. And we have to do it in both definitions. Find slope of tangent line at the point to f of 2 using, we're going to use both definition. Okay, first I want to use the one that involved the h. That's going to be 2 plus h minus f of 2 over h. And second, we're going to use the other definition. Okay, so let's see. So let us do that this way. What is f of 2 plus h? Be very careful. So it's 1. What does f does? It takes 1 over the input. So 1 over my input 2 plus h minus. What does f do to 2? It's 1 over 2. The whole thing divided by h. So now we have to do a limit, which is a little bit. So now my graph is, let me a little bit remind you the graph. So this is my graph. My function is decreasing right there. That's my point. That's my slope. That's my line. And even looking at the picture, we know we should expect a negative slope. So this number, whatever it is, has to be negative. So let us remember, how did we do those limits? As h become close to 0, this is going to 0. This goes to a half, minus a half 0. So I have definitely 0 over 0. So we have to manipulate algebraically. And do you guys remember how did we manipulate? What was the key idea? Okay. We had this numerator, which was really kind of messy. And the idea is really to simplify this numerator. And the only way we can do that is by finding a common denominator. So a common denominator here is 2 times 2 plus h. So we have to multiply by 2 minus 2 plus h. We have to multiply by 2 plus h. Okay. And once we do that, we can combine the denominator. So this will give me the limit. So as you realize, you're back to the limit. And this will become in the numerator. I combine them. I have a 2 minus the quantity 2 plus h. We have to be very careful with our parentheses. Divided by 2 times the 2 plus h. So finally, this will give me the limit as h goes to 0. Now this piece here, if we collect stuff, this will be exactly minus h. Okay, so I don't have to rewrite it. So it's going to give me minus h over 2 times 2 plus h times, this is h over 1. It's going to become 1 over h. Okay, so this is back to familiar territory. Those h's do simplify. And I will get the limit as h goes to 0 of minus 1 over 2 times 2 plus h. As h becomes very small, this will leave me with minus 1 over 4. At least we know it's going to be negative, but that's about all we know. Now let me do the setup with the other definition. So let's see what's the other definition. Okay. Are you guys done? Can I move on? So what's the other definition? So now we're going to use the second definition. Let us see how it changes. So the slope equal. Instead of calling 2 plus h, this 2 plus h, now I keep it x. So that's really the change. So I don't call this 2 plus h. I call this x minus f of 2. That's really what we're doing. But in this case, that's the change of output. The change in input is going to be x minus 2. But now I want a limit. But I want a limit that when what happened? When I put f of x, it means this is my base point. This is 2, and this is my x. What I want is the x coordinate to become close to 2. That's really what I want. That's how my point Q get close to P, by having its x coordinate becoming close, because x is the one changing. And now once we set it up, which is for me the very important step, and then we do the algebra. F of x is 1 over x. F of 2, 1 over 2. X minus 2. And this very much we've seen this. Okay, so now again, common denominator as usual, because in the numerator, so the x minus 2, I don't have to worry about it. I have to find a common denominator here. So the common denominator is 2x. So it's going to give me 2 over 2x minus x over 2x. That's my common denominator. So finally, I will have the limit of 2 minus x over 2x verbatim divided by x minus 2. We're almost at the end of the problem. So this will give me the following. The limit as x become close to 2 of. So this is divided by 1. So I can use the property of fractions. It's like multiplying by that. And this is 2x. And this is 2 minus x. And you know, as my goal is to be able to simplify by the x minus 2 to get rid of the 0 over 0. But as you remember, what did we do in this scenario? It is x minus 2. What? Go ahead.
You factor out negative?
I have to factor out negative. So now, as I said, I am in familiar territory. 2 minus x, I factor out that. And then I will have basically the minus 2 and the x. I have to do that to be able to simplify over the 2x times the 1 over x minus 2. Okay, so, sorry. Now those will actually go away, and I will be left with the limit of minus 1 over 2x. I mean, we should get minus 1 over 4. Anything else will be wrong. Now, when x becoming close to 2 twice, will become close to 4, and my answer will become minus 1 over 4. Okay? So the slope is basically minus 1 over 4. Right? So I think that's it for today. Actually, sorry, I'm going to take 2 minutes so you guys will be able to do the homework very easily. So we did the most of it, but forget to mention, not to mention, to do one tiny addition. Suppose I ask you to do the following. Find the equation of the tangent line. Find the equation of the tangent line of the function f of x equal 1 over x at the point 2 f of 2. Okay, suppose I ask the following question. So it's the same idea as f of x equal 1 over x, but now I'm going to find the equation of the tangent line. It will take me just 2 minutes, my apology for that. So this is my function. This is the point P, and this is my tangent line. This is my tangent line. And the question is, I want to find the equation of this tangent line. All right. So how to find the equation of the tangent? We know the slope. Based on our previous work, that's the minus 1 over 4. So that's the slope is minus 1 over 4. And now the point. This is the only point we know on the tangent line. So the point is 2, f of 2. My function is 1 over x. That's the point. So now I know the slope and I know the point. So now the equation would be y minus a half. It's the slope times x minus 2. And that will be the equation of the tangent line. Written in point slope form. And then if you want to write it mx plus p, you just do the math and you will get it. All right. Okay, so that's it for today. Please do the homework. It will be in my lab homework. Please do your homework for tomorrow. Don't wait to do those homework, because I want you to stay up to date with all the idea we will be developing starting today. All right. Any questions before we go? Any questions? Okay, thank you for staying a little bit longer. Bye-bye for now.